just for the airport's move this door saying.
Are we ready? Hi, my name is Greg, W0TLM. I have a lot kind of to cover this morning. We're going to talk about safety related to antennas. Primarily, there's three or four things. There's three or four things we're going to go through in a little more detail. Part of this will be lightning protection and grounding. So, general safety, use some common sense. Most of us are at an age where we're much better off on flat ground than we are on a roof or on a tower. It is possible to fall if you're building an antenna. Larry's got an antenna in his attic, and it's easy to slip on a joist and go right through the ceiling. And not only will you have to repair that, you're going to have, you might hurt yourself. So be careful. It always makes sense to think whether you should have safety gear with you. OSHA has requirements that if there's more than a 6 foot fall risk, you're supposed to be tethered. I've been on my roof, I'm never tethered, but if I had a steep roof, I'd think about it. It makes sense to maybe have someone nearby that knows where you are. I've seen ladders fall, and then the person's on the roof and they can't get off the roof. And I've heard of people having to call their wife to come home from the store because fortunately they had a cell phone with them so they could call their wife to come home and put the ladder back up so they could get off their roof. So, and of course you all know that even a short fall can really cause problems at my activity. Power lines, they're dangerous, so be careful. I found a sign that said don't work within 10 feet of overhead power lines. I think that's a pretty good safety tip. Keep everything away from them. Don't assume that they're insulated. Don't assume that your fiberglass or your wood pole is going to protect you and act as an insulator against the current that's going through there. It may not. It would help to know a little bit about electrical first aid, and don't work alone. But even simple ideas like, well, I'm just going to run my dipole or my infed half wave, and it's got to cross the power line, but I'm going to be 15 or 20 feet above that power line. I'm going to be completely safe. Well, wires break. I lost an antenna last week in the wind at my house. And when that wire breaks, it falls down, it's going to cross that power line. And it's going to create a danger. And so I would say steer clear of the power lines with your antennas. If you're going to use a tree, which I do, there are many ways to get up there. It's a lot easier if you use like an arborist slingshot. Tim's got one of those. Maybe he'll show it around later today. Sometimes we use pneumatic launchers. I've heard of people doing with bow and arrows and slingshots. There's all kinds of different ways to get it up there. But some people will actually climb the tree. And to do that safely, you need to have two harnesses, so that you're a harness and then two lines, so that you can leapfrog over branches that are in the way. It is something that you're better off having someone who knows what they're doing do it if you're going to go that route. You can, of course, put the eye bolt all the way through. That'll prevent you from killing a tree. Some of the trees, the bark is not thick enough to protect them. So if you use a tie-off that goes all the way around the tree, you can choke the tree and ultimately kill it. So, like I said, tree climbing is not trivial, like we used to think it was when we were kids. I would, just as an aside, try and plan a system that will allow the trees to sway in the wind so you don't lose a line like I did. This is one of those ways to do it, where you connect a pulley. I do mine where I shoot the line through. I have a pulley, and then I have I think it's called a halyard, that ties to the insulator. And so I end up with 4 times as much rope as you would if you could have someone just climb a tree. With masts, once again, it is not trivial. You can have freestanding towers, and they have to be engineered so that they will stand. But typically, we will use a guying system with the smaller towers or with a tall mast, even a 30-footer. Sometimes you will guy them. Use appropriate anchors, use appropriate tensioning, and use appropriate material. And if you're using wire materials, those will affect your antenna performance. So there are ways to do that. You need to spend some energy. The message here is spend some time thinking about your guying system if you're going to guy your mast, and think about the tensioning, and you can go learn more about it. Towers, completely different set of problems. Lauren's going to give us a presentation in a few months about his experience building a tower and installing a X-beam on top of the tower. But tower climbing safely is something that you need to learn how to do. I would hire an expert to do it. There are people out there that will. But you need a harness, you need proper clothing, you need the right kind of tools, you need training, you should have assistance. And like I said, you can hire someone, make sure they have insurance, make sure they're properly trained. Don't just send the neighborhood kid up there to adjust it. Not safe. Crank up and tilt over towers have additional risk factors associated with them. That tower can come crashing down if you happen to have your arm through when it comes crashing, sliding down and collapsing. Big problem. Or if it falls over because you don't have the proper safety gear in place, it could land on something. So pay attention to those. Wind loading is an issue for towers. Lauren is in the process of building his tower. He had a mechanical engineer calculate what kinds of pad he needs to put on, where he needs to locate the guy wires, how the guy wires have to be anchored, all those things, because there's all these forces. And of course, there's a fair number of engineers in here, and they think, well, I used to know how to do this. I can probably dust it off and do it again. I can answer that with a clear, well, maybe. But you're better off you get someone that knows how to do it. It's not a trivial calculation, and if you are wrong, it can be fatal. So be careful. They do wind load calculations as a matter of requirements in the county building manual. In Douglas County, which is where I live, you will calculate wind speeds of 105 to 130 mile an hour. And your tower needs to stand. I think Lauren said that you calculated his at what, 135?
135 for a 6-second gust.
6 seconds, which is a fairly long period of time. Now, once again, if you do a guide tower, that can help ameliorate some of those issues. But if you're doing a freestanding tower that's unguided, you're going to have a pretty good chunk of concrete at the bottom of that tower. So there's a lot of rebar. This is a picture of a rotating tower that collapsed. And it could be caused by wind, could be caused by ice. It could be caused by a lot of things. There's actually a guy that studied it, and they found that construction errors were the leading cause of problems. Ice was the second leading cause. Winds, aircraft, anchor failure. Some of those construction errors are assembly problems where you are bringing up the antenna to put on the tower. You've got a person on top of the tower. You've got all these extra weights up there that you have to deal with. And if it wasn't engineered correctly to deal with that, you can have all kinds of problems. So in the tower erection, that's not the final time you think about tower safety. You really need to have a safety program in place where you do periodic re-inspections of everything. The guy wires, the guy wire anchors, the concrete, everything that you're going to be dealing with in a tower. The K3LR has a huge antenna farm in Pennsylvania, and they have antenna crews out there like 3 weeks of every month. And they're just inspecting the guy wires and making sure everything is still, all the bolts are still tight. It's a mess. So kind of the general takeaway from this is use common sense. And by this stage in life, you should have a lot of common sense. If you slow down, stop and say, I want to think before I do something. Be aware of everything that's overhead, or if you're going to cross power lines, you do not want to run that risk. Flow risk, safety gear, don't do things you don't know how to do, and I would definitely hire an expert if you can afford it. And if you can't, then I would find people in the club. There are younger hands who are trained who will help you. But, you know, think about you climbing that tower and you're up 60, 70 feet in the air and your knee locks up or your back goes out or you suddenly feel lightheaded. You don't want to be there. It's a problem. So, RF exposure is another big antenna risk. So, you may recall that in May of 2021, the FCC changed its rules on RF exposure. They didn't change the RF exposure limits. They just eliminated the automatic exemption from doing the calculations. And as a result, if you make any changes to your station, you are supposed to do the RF exposure compliance check on each band that you're going to be operating, and you need to keep a copy of those calculations in your permanent records at your station. You do not give them to the FCC, but you need to prove that you're in compliance. Why does anybody care about RF exposure? And as you can see, RF exposure can cause burns. And so it's dangerous. You don't want to go there if you can avoid it. So evaluation. So there's two sets of limits. There's in the controlled environment, which is occupational too, or in the uncontrolled environment where the general population can be. There are different limits for those environments because of the assumptions of the people that will be in those environments. What you're measuring is the maximum permitted exposure. I don't think it's a trivial calculation, but there are calculators available online that will do it for you. It is possible to be exempt from these calculations, but you have to run through a calculation to determine whether you're exempt. And so I would suggest just using the online calculator to calculate that you're in compliance. This is a chart that shows the exposure levels, and you'll notice that in the lower frequencies, the permitted exposure level is dropped down. There's also kind of the math here. You can see the levels, different field strengths, magnetic field strength, and power density. It's way beyond this talk to get into how it's actually all calculated. Here are some online tools that you can use. I would use them. I did mine last year. It was, I think, a little kind of confusing. You're comparing isotopic radiators and idealized dipoles in free space with your actual antenna that has grounding factors involved, and you're trying to use EasyNIC to figure out what I have going on. It was not an easy task, I didn't think. But Lauren helped with this slide. His suggestion is, of course, start with the highest frequency at which you're going to be operating and see if you're in compliance. And the odds are, if you're in compliance on that, you're going to be in compliance on all the others. Yes, Lauren?
Just a slight correction to what you said, not necessarily the highest frequency you're going to be operating, because that range of where the level was the lowest started at 10 meters and went up to about 300 megahertz. My suggestion would be to start at 10 meters if you're operating, because that's going to be a worst case. Not for the amount of power that you might be using. And the message to this is, assuming the worst case, exposure time, the worst case, gain of your antenna, the worst case, and you will probably pass.
Yes.
Unless you're running a super high station and your highly directional antenna is not 150 feet up in the air. Just assume that, and it will probably pass. If you find out you don't at one of those frequencies, now go back in and try to figure out, well, am I really operating 100% of the time? Am I really, is the mode, the modulation that you're using really the best case? The point is, it's really not that hard to pass this if you run through the numbers. Don't worry about it unless you find out who you don't pass. That's what it is.
Right, could everybody hear that? So the idea is, because this is a safety feature, a safety calculation, assume the worst possible case because you want to comply. You want to be safe. You don't want to harm your neighbor. You don't want to harm yourself. But most people are going to pass this test unless you have high gain antennas, you're running power, or sometimes people have antennas in their operating shack because of HOA restrictions, and so they're really close to the radiating elements, and they want to make sure that they're doing it safely. You're going to hear this afternoon about these antennas that are magnetic loops, as we call them. And if you have that set up right next to you and you're transmitting at relatively high power for those magnetic loops, there can be some dangers associated with that, so you need to run through the calculations. Everybody's going to have to be in compliance with this rule in May of 2023 if you don't make any changes to your station between May of 2021 and May of 2023. Once you make the changes, then you need to come into compliance with the FCC rule. And as Lauren suggested, if you do the calculation, which I did the first time, and I wasn't compliant on any band as far as I can tell. Well, it turned out I was giving the wrong information to the calculator. And so it was telling me I had a problem. Well, I didn't really have a problem. So make sure that you're using the right information in the calculator. You can use antenna modeling software like EasyNIC to more accurately calculate what your antenna will do. But look at the requirement. It may be that you need a dipole in free space calculation and not your actual calculation from your dipole at your window. You can move your antenna or alter your antenna or use a different antenna on the frequency where you have a problem. You can cut back on your power. Don't run 1.5 kilowatts on 6 meters if 6 meters is a problem for you. You can change your duty cycle and talk less, adjust downward how long you think you're going to be talking to a more reasonable level of how often you think you're going to be speaking, because that affects the amount of radiation that's coming out of your antennas. If you ultimately find that you do not pass, then you're going to have to do other mitigation, such as fencing it off and putting up required signage. And then you can also not operate when people are around. Now, I have a friend that I know did do these calculations, and he ran a contest last year, and he built himself a vertical Yagi. And he did that with 30-foot high fiberglass masts at the correct distances apart. And he phased those antenna elements, and he ran 1.5 kilowatts into them. And he had it in a residential neighborhood running across the front yard. Well, you want to make sure that you do the calculation before you fire that up. Fortunately, he was firing it up late at night, but he was required to do the calculation, didn't do it. So the takeaways are the FCC is going to require you do these calculations and you keep them with you at your shack. You don't file with the FCC. Just keep your analysis so you can prove that you're in compliance and you've done the test. The exemption isn't really that much harder to do than the actual calculation, but if you're going to do it, you might as well just do the actual calculation, find out that you're in compliance. There's online tools, and if you initially fail, go back and make sure you fed the right type of data in, make sure that your assumptions about operating duty cycles is correct, and then you can maybe change the antenna you use on a band if that's a problem. You can relocate your antennas, that kind of stuff. Is there any questions on RF exposure before I move on?
Yeah, what percentage of your output power at the antenna factors into RF exposure? Like you said, some of them are running 1.5 kilowatts. Most of us are not going to have towers. We're going to put a dipole in a tree, or we'll have a tripod or a roof. And most of us are going to be running 500 watts or less on HF.
If you run 500 watts or less on HF through a dipole in the trees, you're probably going to be fine with the calculations. If the tri-bander, you're running 500 watts and the tri-bander is 15 or 20 feet above your head, you're probably going to be fine.
Okay. QRP, I mean.
QRP, it's not going to be an
It's
issue.
not going to be an issue. Okay.
Okay, so the next safety item for antennas is the National Electrical Code. And there's a lot going on in National Electrical Code, and it might have been easier to read if it had been in Pig Latin. But I'll give you just some highlights that jumped out at me that affect ham radio operators. First of all, you cannot attach your antenna to the electrical service mast, which is that bit of conduit that comes up out through your roof, and then the overhead wires come in. Now, most of us live in more recently built homes, and so the service is all underground. You don't even see those overhead wires. But some of you may be in a neighborhood where you do have those overhead wires. And as we talked about earlier, with just kind of the common sense, it's better not to cross over that power feed. There's a minimum requirement of 2 feet of clearance, but when you look at the way the utility companies do that, they have really thick supporting guidelines that hold those electric cables so that there's no chance of there ever being shorter than that 2 foot gap. We don't do that typically with antennas. It's just a single wire or a pair of wires. So you don't normally have that added protection. So I would just avoid crossing utility power no matter what. I hadn't paid enough attention, I suppose. There's a minimum required diameter wire that you're supposed to use for antennas. And it's 14 AWG if you're under 45 meters or 150 feet. And it drops down to 10. Now, this is hard drawn copper. There's a different level for copper-clad steel or other high-strength materials. If you use, the solid copper, it'll stretch, and it's kind of a hard thing. Any questions about that? Now, we'll talk about SOTA and POTA later, and a lot of guys are using 22 gauge, 24 gauge, 26 gauge. Most of those people are running QRP loads. So, was there a question? Yes?
For the leading conductors must go through solid, not combustible conduits. Is that the coax feed line needs to go through solid conduit?
Yes, it's supposed to go through a solid, non-absorbent tube or bushing into your shaft. I know a lot of people have come up with different ways to solve that problem, but it doesn't really technically comply with the NEC. I think there's a separate rule on coax itself, but I know that there's a kind of a flat coax that you can buy for entry through a window sash. And it's, it's probably not compliant with the NEC. But. And then the other thing was kind of weird is you could drill through a window pane. And I don't know any hams that have drilled through window panes. And then, of course, this is the common sense thing about lead-in conductors. should be as far away from things as you can get them, so that, you know, the toddler isn't playing with your antenna feed line while you're transmitting, which makes some sense. Grounding conductors must be as big as the antenna lead-in, but no smaller than, this is the hand-drawn copper, 10 AWG, 17 AWG for copper-clad steel, or number 8 for aluminum. They want that protection. We're going to talk in a few minutes. I'll show you lightning protection systems. Most people have a grounding system and a ground rod and lightning arresters, and that will be compliant. And then we'll talk about bonding your grounding system to your house electric ground also. But the bonding wire has to be number 6. So that's a pretty good sized wire. Outdoor masts and supports must be grounded themselves. They're a source of lightning attraction, as you might guess. And then feed lines or lead-in conductors have to go through lightning arresters or lightning protectors, or it's kind of really a surge protector. This is gas discharge tubes presenting a low resistance to ground for the center conductor is what those do. And then if you have a single point grounding system, it should be mounted on that same panel. I'll show you a picture of one of those panels. So the National Electric Code does apply to us. Use your common sense, avoid power lines, do the RF calculations to make sure that you're not violating the RF emission requirements. Most of you will pass. If you don't pass, it's because of a special case, probably running power. Your antenna's too close to you, like an indoor antenna, something like that. Do the NEC requirements and make sure that you comply with them. Yes, sir.
So, I'm holding a tower, a 30-foot tower. Does that typically require a permit?
Well, that's a zoning issue, as well as a national construction code issue. What Lauren just went through this, and he had to get it approved. If you live in a covenant controlled community, there may be covenants that require you. In my location, all the requirements are, of course, have to comply with the FCC rules and the FAA rules. And if the tower is going to fall, it has to land on my property, which means that if I got a 75-foot tower, I got to be 76 feet away from the property boundary. And it also depends on what you're going to be running at your antenna. If you run full power, you may need an electrical outlet at the base. Lauren, go ahead.
It's all going to be, to answer that specifically, it's pretty detailed on where we live. I live in a city that is Colorado Springs, in a zoning area that is public use development, which is those residential homes out with an HS hillside designation. The hillside throws a whole monkey wrench into the approval process. So I had to work with city zoning in order to give permission to build it, because they were concerned about view lines. Just, for maintaining view lines. They approved it under the condition that regional building would approve it, because it's a structure that's being built. It turned out regional building said, not attached to us, don't care, which surprised the heck out of me, but okay. And then it's the HOA, of course, that but you're right. There are, from a construction standpoint, there's all kinds of safety stuff. So even if you don't get approved, you better be aware of what the standards are for building and for protecting it from windows and such. So if there is a possibility of falling on anything other than your own insured house, you're covered, because that would be open. If all goes well, there will be 3 sections, 30 feet with about a 5-foot wall. So the total height's going to be about 38 feet.
But yes, you need to check.
I'll be happy to talk to you.
You need to confirm any local requirements are complied with, and that would involve construction requirements as well as zoning requirements, and then if you're in a community that has covenants, covenant compliance. And not all HOAs preclude antennas, but a lot of them do. And even if, so if you're permitted to have one, there may be limitations on what kind of a tower you can put up. So let's see. I think we're ready to move on to lightning protection, which is really, we're not going to be able to do as much depth as I'd hoped, but hopefully we'll get through it. Lightning is a very, very, very common event. This is a map showing lightning strikes. So it happens frequently, about 44 times a second, or 1.4 billion flashes a year. So it happens all the time. Now, a lot of that never touches the earth, never affects us directly, but you'll hear it when you're on the HF bands, and you'll hear these crashes all the time. They tend to be relatively short-lived events, but as Lauren would point out, there's a huge amount of voltage and current associated with a lightning strike. And we want to design our shack and our antenna systems and our towers to make it safe for us, our shack, and our equipment. Most strikes are 3 to 4 impulses separated by very, very, very short intervals. Look at the size of the average strike, 18 kiloamps. I mean, that is huge. They range between 3 kiloamps and 140 kiloamps. I mean, that's massive. So the interval between pulses, 50 milliseconds, which isn't very much. It's, as far as I understand it, it's really pulsed DC, but it produces it produces RF all the way up to 100 megahertz. So you have to be thinking in terms of our earlier discussion about impedance. We're going to talk about that again coming up. So with this RF energy, you have to consider the reactance component as an element of impedance or resistance in the design of your system, because that reactive component can increase the impedance or resistance and can affect where that current's going to want to flow. So there are lightning detection systems out there. Who knew? And you can program your Raspberry Pi to give you an alert when there's lightning nearby, and you can set the distance away, and there's all kinds of fun things you can do. As hams, there are iPhone apps. You can build your own. There's websites. It's kind of fun if you want to get into it. So the goal of a lightning protection system is to create a pathway so that the current will flow where you want it to flow and not through your shack. And you want to also use that system to prevent large voltage differentials between different points in your shack and in your antenna system and feed line system, because those large voltages will encourage these large currents to flow over anything that will allow conductivity. And the way this is normally handled is you create a zone of protection, and everything that you want to protect is inside the zone of protection. Now, I've got kind of a confusing diagram here, if you will, showing the typical things that you might have associated with your house and shack that have connections to the outside world. At the top, TV, maybe you have a clock. We get down into more ham radio stuff, a rotator, a transceiver, a power supply, maybe an amplifier, maybe an antenna tuner. All these things are connected to the outside world many of them through the three-prong safety plug, which we'll talk about in a minute. Some of them are connected to the outside world through coax. Your rotator is connected with its control wires. And so all that stuff is a possible path into the shack for these huge voltages and maybe huge currents. There's also, you might have a modem, you might have, your modem might be connected through Cat5 and a router directly to your laptop or your computer. You may use Wi-Fi, so maybe it's not connected there, but that modem and your router may be connected to the outside world. So let's go back and talk about, there's really three kinds of grounds that we run into as hands. That is the system of earth ground, or the symbol for earth ground. The one we saw earlier with the three diagonally spaced lines is a chassis ground. So there are different types of grounds indicated by the schematic. In any event, the green wire in your house is required by the NEC, and it is a ground, and the idea is to take any kind of a short circuit that affects anything that's plugged in and allow it to have a ground exit. Instead of through you, it'll go down that copper wire and hit the earth ground for your electrical system. Our ham equipment, if it's plugged into the three-prong plug in the wall, all that's taken care of. That's an AC safety ground. There are some older homes don't have the three-prong plug, it's only two. You're really supposed to take the three-prong adapter and then connect that third prong, the green wire, to the grounding system for your AC ground. So in my house, what happens is that green wire has a direct home run to my service panel. And then at the service panel, it's grounded to the neutral, and then it's grounded to the grounding system for the AC, which in my house is the copper cold water inlet. Most newer homes, they're going away from connecting to the copper water pipe and using separate ground rods because they're using these PEX and plastic pipe systems. Yes, Warren?
I have no ground rod, no copper for my grounding system. The single point ground is actually tied in with rebar in the foundation.
And there is a rebar system of grounding that some people have. I don't have it. So.
That's probably the most likely way on anything built in the last 20 years has been constructed.
Right. And this grounding system for your AC ground affects the potential in your shack on the AC grounding portion. And this is what we're going to be bonding to when I talk about bonding your perimeter ground system to your electric AC ground. So the idea is we're trying to create a perimeter around your entire house that is at ground potential. And I always thought of ground when I was younger as this sinkhole that would just suck up all the extra current that we could give it, and it would just disappear. It just was gone. Well, there's resistance in ground, and there's quality of ground, and it takes a while for all of that energy to dissipate. And it dissipates over distance. And so what we do is you put in a ground rod, at least one, preferably at least two. Normally it's an 8-foot ground rod driven all the way into the ground, and then it is connected to any other ground rod. The preferred system is to do a perimeter of your full house. And if you're using 8-foot ground rods, you want the ground rods as close together as you can get them where they still work. And the reason why you want to do that is because the connections between them have inductance, and at RF frequencies that will act as resistance to the current flowing down that connecting wire. So the shorter that is, the better. And then you would put in, the recommended is with an 8-foot ground rod, 16 foot of separation, because that gives you the maximum amount of grounding for the distance apart. If you have them closer than 16 feet, they work a little bit against each other, is essentially what happens. So when you connect your ground rods together, you may recall that the grounding wire for your home AC is like a number 6 AWG. It's like not quite a 1/4 inch in diameter, solid copper. Well, if you use that for your lightning protection system, that presents an identifiable amount of surface area. And this pulsed DC and RF energy runs down the outer skin of that conductor. It doesn't run through the center, it runs on the outer skin. So if you, instead of using a rounded copper wire, use flat copper strap, you present more surface area, and that has the unique ability of lowering the inductance, which reduces the resistance caused by that inductance and allows the RF energy to flow better. So the recommendation is to use 1.5 inch copper strap to connect those perimeter ground rods. And you need to have a real solid mechanical connection, because at 15 or 18 or 20 kiloamps, it will literally explode a soldered connection. So the recommended way to do that is to use a mechanical connection, which is like bolts, and you crank them down tight. There's another way that's kind of fun that I don't know, maybe Stu did it, but I don't know many other hams that have done it, and it's exothermic welding. And you pour a powder in, and then you pour an igniter powder in, and then you light it off, and it heats this thing up to some unbelievable temperature, and it welds it. And that weld is strong enough to take that huge spike so that it won't fly apart. Now, the idea of the perimeter ground is this. When you have a lightning strike, there's kind of two events that I think of. One is, it's a direct hit. It hits my shack. And then the perimeter ground isn't really going to do a lot to protect you there. But lightning can strike nearby, and it drives this huge current into the ground at that spot. And then that radiates as it's trying to dissipate all that electrical energy. It radiates. And as it's coming toward my house, it presents what I think of as it raises the potential, the voltage potential, which will encourage a current to flow. And so if I have surrounded my entire house with this perimeter ground, when that electric charge comes in, it'll get spread out around the whole house, and then it will all rise together at approximately the same time. And I say approximately because, as we learned in the last talk, electricity through conductors doesn't flow at the speed of light. And so even a few nanoseconds can create an opportunity for a big voltage differential, which can create an opportunity for current flow. So that's why they want a full perimeter ground. I only know one ham, and I think Stu's the one, that put in a full perimeter ground. And what I've done in my house is a partial perimeter ground, and that's better than nothing. So, let's see. One other requirement we talked about in the NEC is to bond that perimeter ground, that outside ground, to your antenna primarily, to bond it to your electric system AC ground. Now, the way I did that is I ran copper strap and connected it to a copper water pipe, cold water, so that it then is bonded directly to my AC ground for the house. So when that voltage comes from that stripe that's away from my house and hits my perimeter ground, it raises the potential energy there, raises that potential. My ground for my AC is also raising at the same rate, so there's not a differential, so it doesn't encourage current to flow between them. If it's not bonded, it could rise faster than the one for the house, and then there's a differential, and it will seek any conductive path to equalize that potential difference. And if it happens to be through your radio gear or through the house wiring, it will fry everything in its path. So that's why you're trying to do this. That's why they require it to be bonded. So this is kind of a pictorial presentation of all that. So your tower has to be separately grounded. You notice that they have 3 ground rods, and then there's looks like an antenna cable. It's probably hardline or coax running over to another ground rod driven into the ground, and then that ground rod goes around. Now, in this diagram, it only shows it going up and above, and everything else is on the other side of that grounding system. And then there's 2 main connections. One is this AC power panel, which is all your AC to the house. Remember, it's grounded separately. And then your entry panel, which I'll show you a picture of an entry panel. And since they're bonded together, the potential rises and falls at the same rate. So when you get this huge increase, everything goes up and comes down, and it doesn't encourage current flow in your shaft. So I'm going to stop here for a second. Anybody have questions about this so far? Yes, sir.
Not about this particularly, but I have a stucco house, so I've got chicken wire all the way around. Is there any recommendation about grounding for that?
You have chicken wire around.
That's what the stuff
It's
is.
Oh, stucco. Yeah.
Yeah, so you got chicken wire and then you got the stucco.
Well, we'll talk about that, because one of the problems I had at my house was that when they installed my cable TV and my phone, they sent out a repairman from the phone company or the cable company, and he wasn't an electrical engineer, and so he drove a little skimpy ground rod in the ground and connected it right there. Well, it wasn't bonded to my electrical system, which is a requirement. So there's a possibility of a differential as a result of that. So the real cure for me is to bond to that ground rod also.
What about an AC, because it doesn't meet the size of the wire, for one thing, and you can be pretty certain that mesh is not grounded to the single point system.
Oh, yeah.
Right.
Yeah, don't rely on your chicken wire to ground your mesh.
Don't worry about it.
No. Don't worry about it, don't try to use it, it's more of a fear than a cage.
Yeah.
It is,
Okay, I got one more.
Yeah, I've got a whole house lighting protection system.
Good.
That was verified by Operator Labs, there's 17 now, gave some messages to them. And I bound my antennas just hang off my chimney, and I bound my antennas to that.
Your antenna's hanging off what?
Oh, my chimney.
Off your chimney. Yes, your antenna needs to be grounded. It's a requirement of the NEC. It'll be dropped down to your perimeter ground, which will be bonded to your AC ground. You'll be fine. But you need to ground it. It's required.
What I'm asking is, since my lighting protection system is already within inches of it, can I just bond into that?
I think so. Okay. Now we're going to move on to a single point grounding system. You learned about this when you studied for your tech and general license. The idea is that you're going to have all of your pieces of equipment in your shack with a star-shaped pattern ground to a single point. or you're gonna set up a bus bar and connect it all to the bus bar, and then you're gonna have the bus bar go to your ground. You're gonna connect that single point ground system to, in my case, I have an entry panel that is grounded to my perimeter ground system. That single point ground system at my entry panel is connected to my perimeter ground with 3-inch copper strap, not wire. And the idea is to permit all of that high RF energy that comes from a pulse lightning strike to get to the ground system over the lowest impedance I could present to it. And that was 3-inch copper strap. There are suppliers that'll sell you that stuff. Yes, Warren?
Just something to think about, and you mentioned it, but it bears re-emphasizing, is that it's not the resistance of the wire that causes the problem that you said. It's, as you said, it's the inductance of that, because the voltage is determined by the rate of change of the current divided by the frequency. And if you've got if it's a 1 megahertz signal, and you pointed out, could be going up to 100 megahertz, but at 1 megahertz, you're dividing that number by a million, or sorry, 1 million. Well, that's 100,000 volts. If there's 1 amp of current change, 1 amp of current change in an inductor could be up to 100,000 volts.
Right, we're talking about the its impedance when you're talking about an inductor, and it's a reaction. It looks a little bit like resistance to the simpleton here, but he's right. It's technically not resistance, and it does create huge differences. So this is a ground panel. We're kind of running out of time, so I'm going to jump ahead. It's a solid copper plate. It's inside a waterproof box. There are drill holes underneath to allow moisture to flow out and bring the cables in. There's a solid conduit to the shack. Looks like in that. This isn't mine. This is one I took from KF7P in Utah's website. He supplies these. You can buy them. They're very nice. These are lightning arresters. That's an alpha delta version. There's a threaded plug that goes into those. They are, you buy different sizes depending on the output power of your ham shack. So if you're going to be running 1.5 kilowatts, you want them sized to say 2 kilowatts. If you're going to run 100 watts, they have them at like 250 or something. You can see that they have a station ground connected to that flat ground plane, and then they also have this braid, which is an RF ground for your shack. I use that RF ground through 1-inch copper braid that is covered with this silver stuff. I don't know what that is, it's lead or what. In any event, that's what I would recommend using to enter your shack. It would require drilling a hole through the wall into your shack. You can put a fancy faceplate cover when the coax comes through. It's really fun. Here's a couple pictures of different pieces that we talked about. Lightning arrestor upper left, a bus bar in the lower or mid left, the copper or the braid that I use for RF ground in the shack, and then the copper strap, and they come in different sizes, and you can buy whatever length you need. One school of thought is, well, just disconnect. There's lightning nearby, I'll just disconnect. And so you put those fancy, real quick disconnect PL259 connectors on, you jerk those off, drop the cable on the floor, and you're home free. Well, maybe, but think about all that voltage on that line in your shack with no place for it to go. It may jump, and it may jump a distance. So that's not the safest way to do it. Everybody that I've read said if you're going to disconnect your coax, disconnect it outside the shack. And so I guess that means if you're going to disconnect it in the shack, you throw the ends outside the shack. Now you can buy grounded antenna coax switches, which will provide a way for that power or that current to go to ground, and that will help. They're really, I don't know if they're designed to be a primary lightning detection thing as much as a static discharge dissipator.
Remember earlier, if that line looks like a quarter wavelength, that short circuit at the grounding outside, if it travels down that in your quarter wavelength, it's an infinite impedance if it's in a circuit, and that voltage is certainly high enough to cause potential arcing.
Right. So in any event, so I don't necessarily recommend, I would think through whether you want to just disconnect the cables. There's one of the quick disconnects, there's one of the grounded coax switches if you want to know what they look like. Now there's another thing that's always interested me, and that's a piston-driven disconnect, and I just leave that as a thought. Someone spent a lot of energy in mechanical ability to connect together. One last little comment. So the lightning arrestor is designed to short the center conductor to ground in your coax. And it does it with a gas, and once the voltage level rises to a certain level, it becomes conductive permanently. And what it does is it shorts the center to the shield. And if it's mounted on the ground that goes right to your earth ground, then everything stays at the same potential. Without that lightning arrestor, the center conductor would be at a different potential than the shield because the shield's at earth ground. So without that, that's connected then to your radio, separated by the thickness of your dielectric, and you get this huge voltage surge. One potential goes way up, the other one stays where it was. It's going to want to cross that with current so that it equalizes, and it's going to do it right through your rig, and that's why the lightning arrestor is a marvelous thing. We talked about that. I strongly recommend that you buy this book. It was just re-released in a second edition by Word Silver, Grounding and Bonding for the Radio Amateur. It's, I don't know, 25 bucks or something. It's a wonderful book to learn about how to ground your station. So, lightning protection, high voltage, high current event. I have in there, it's relatively short-lived, but it is. The problem is you're dealing with such massive voltages and currents that even a short event, maybe an eternity, I think was the email I got back. You want to create a perimeter system. I would use the strap instead of the wire because of the difference in the inductance, which has reactive impedance, which I think of as resistance, and I know that's wrong, but which prevents it from transmitting. Use a single point ground system, use an entry panel connected to your perimeter ground, and then make sure you bond it. Questions? Okay. I guess we're done.